So section 4, we're looking at sampling distributions and the central limit theorem. In all this will represent really just one new concept, but a very powerful theorem, the central limit theorem. Now, in mathematics, once we have a theorem, typically someone has spent much of their life's work to create that theorem, and sometimes often over several generations. So it's a powerful tool that we will have at our disposal, and it'll show us that everything we've been learning about the normal distribution is going to be even more valuable. So let's look at what a sampling distributions are. What are they? Well, whenever we take random samples from a population, those samples we can create statistics. Remember, statistics come from samples, parameters come from populations. So we can use any of the statistics we can create from a sample, and then those statistics become like a new piece of data. They are used to make a distribution. In this lesson, we're going to be focusing on using the mean as the statistic of choice and looking at how the standard deviation for this sampling distributions of the mean are affected. And so we'll be able to get the mean and the standard deviation of these sampling distributions. So sampling distributions of sample means. A little bit of overuse of the word of sampling, but what is happening is we are from a population that will have its own mean, the mu, and it will have its own standard deviation, and we recognize these as population mean and standard deviation because there are no subscripts. So when we just have mu or sigma, these are population parameters. We pull out samples, and here we've got 5 different samples, and each of those samples will have its own mean. The mean of this sample, mean of that sample, each one has its own mean. And so that gives us 5, if you want to think of it, 5 new data points that we can use to make a new distribution. Let's take a look at an example of how this works. And we're going to do this by basically doing an experiment through the computer, having an applet. The smaller link here is an actual video, as it states, of someone using the applet. So you're welcome to look at that. It was about 9 minutes long. I watched it. It was enlightening. In fact, it taught me how to use the applet. But let's go ahead and now let's open up this applet, and let's see if we have enough room in here to fit it in to this window. So this is sampling distributions, and what we're doing is at the top there's a room for 4 different graphs. The top graph is a population, and we'll see it currently is set as a normal distribution, but we can see we can do a uniform distribution, a skewed distribution, or we could do a custom where maybe we can make it as funky as we want. We're going to just go with the normal distribution, and what we're going to see is we're going to take sample. Here is the size of the sample. It's 5. Let's go with 10 just so you could see it a little bit more. So we're going to take 10 pieces of data out of this population, randomly chosen, and it will be animated, so we'll watch this. So we start seeing data points being randomly created, and then those 10 pieces of data are added together, divided by 10, and it gets us a mean, which we're now getting one little piece of data, if you want to call it that, into this new distribution. We do it again. We get 10 new pieces of data randomly chosen, so they could come from anywhere from this distribution. The 10 data values are added together and divided by 10, and we get another piece there. And we can see we're getting a median that's 15.5. We'll see these go up. It's 2 repetitions, taking 10 data points as our sample, size 10. Let's do it another time. Let's see. Sometimes we'll get some way out here, but notice it's rare. The probabilities are higher that it'll come from the middle, and we're going to build this distribution as we go. And again, each time we do it, we're adding one more piece of data, so we're up to 4 now. This would be the 5th one, kind of spread out, but again, a lot mostly coming from the middle, because that's the highest probability, right? And we just keep doing this, and we do it maybe one more time, 7 times. Okay, now we're getting some stuff way out there. That occasionally happens. What I'm going to do is I'm going to click on the 5. What it'll do is it'll draw 5 samples, calculate their means, and so then we'll add 5 pieces of data to the new sample, the blue sample, as we go. So there's 5. It speeds up the process a little bit, and we start to see the distribution changes. How about we go for 10,000 samples? This will help. This will go much faster. But again, remember, it's going to take 10 pieces of data out of here 10,000 times and calculate the mean. So we're going to add 10,000 pieces of data, and what we start to see is, yes, it's looking very much like a normal distribution. This is the distribution of the means of the samples, and it does look normal. Notice what's happening. The median of the population is 16. That has not changed. The mean up here, sorry, not the median, well, the median also, but for our distribution of means, our mean is also 16.02, but basically they're going to be equal. That's what the theorem says. The mean of the population, that's what the mean of the distribution is going to be, the distribution of means. Notice the standard deviation, it's for the population, it's 5. For the standard deviations of the distribution of means, though, it's 1.64. We're going to see what that becomes. So the standard deviation does change. It's going to become narrower, we're going to see, and we've got a formula that'll do that. But what I want you to understand is what's happening is from this distribution, we end up with a normal distribution that is it's a distribution of means. So we take those samples. What is interesting is, I'm going to go with a custom one and just show you, we've got a type of a distribution that is not normal at all. I'll make it bimodal. The same thing's going to happen if we take enough samples. And let's go with a larger sample size from the beginning. So this is 25 pieces of data slowly coming out all over the place. We'll do this many times, and then it's going to take the mean of those 25 pieces of data, and we go there. Let's do it 5 at a time. Let's do it 10,000 at a time. A couple more. Let's do it 100,000, and we still, even though the initial parent population is not normal, not even close to normal, our distribution of means is normal. And we're going to see that listed as part of the central limit theorem. And notice here, the mean of the parent population, the population is 16.88, and the mean of our distribution, as long as we took a lot of samples, 16.88. Okay, but notice the difference in the standard deviation, 8.94 here, 1.79, and we're going to see how we can actually calculate the difference between those two. Okay, so we're going to go on back to our presentation here, and what we see is, or what we're going to summarize, is when we're doing sampling distributions of sampling means, the average of the sample means, and notice the notation here, mu with a little x bar, this is signifying that this is from the sample, that it's the same, identical, equal to the population mean. So we see this statement here, the mean of the sample, that's this first one, is equal to the mean of the population. That's the second one, just the mu with no subscript, that's the population. However, the standard deviation does undergo some transformation. So this sigma by itself with no subscript, this is for the population, this is from the population. And to get the standard deviation of the sample means, it's related by this formula. The sample is here, sample standard deviation is the population standard deviation divided by the square root of the size of the sample, n. N equals size of sample. Okay. All right. So that's definitely something you're going to want to have in your notes. The mean is always going to be the same, so that's not going to change. If they give us the mean of the population, that's also going to be the mean of the sample, and of the sample means. And then, but for standard deviation, we have to divide by the square root of the sample size. So let's see how this works. Before we see how it works, two little rules that come into play. First of all, this works for any type of distribution, and we see here we're listing the one that's definitely not a normal distribution. This will work for any distribution as long as the samples are taken of a size 30 or larger. So that's kind of one key point. 30 or larger than any type of distribution, its distribution of sample means will be normal as long as n is greater than 30. Okay, what that does, it means we don't even have to know what the population distribution looks like. All we have to know is its mean and standard deviation. As long as we take a sample larger than 30, then we can analyze the data of the distribution of sample means with a normal distribution. And it all follows the same. We've got the mean and the standard deviation, that last page. The relationships are the same. So the mean of the sample means is equal to the mean of the population. However, there's that relationship in the standard deviation where we take the population standard deviation, shown here, and divide by the square root of n, the size of the sample. And one other important aspect of the central limit theorem is if the population itself is already a normal distribution, then we can use any sample size. We don't need to use 30. It can be smaller than 30, it could be larger, whatever. But definitely it doesn't need to be 30, and the sample means will be normally distributed. So normal goes to normal regardless of sample size. But if the population sample is not normal, then we need a sample of at least 30 or more. Well, that's what at least means, right? Okay. Now let's get into some examples. So here's one. We see a distribution here, distribution for all sleep times. This is a study which analyzed the sleep habits of college students. They found that the mean sleep time was 6.8. So we're given the mean here and a standard deviation of 1.4 hours. They took random samples of 100 sleep times. So the samples were random, which is important, and there were 100 of them. They're drawn from the population, and the mean of each sample is determined. Find the mean and standard deviation of the sampling distribution of sample means. Okay, and sketch graph. So here, this is the population distribution, which is not normal. It's kind of got that shape, but it's skewed, right? So it's not a normal distribution. So the population parameters of this sleep population of college students is taken from here. The mean, and notice this mu is giving us the mean, is going to be 6.8, and the standard deviation given to us is 1.4. So we're just going to write those down because we may need those. The sampling distribution, the means are going to be the same, so we just there, we'll come back here. The means will be the same. So that comes down, that's going to be 6.8. The n is a sample size, and we're told the samples are 100. And the standard deviation comes from the population, 1.4, divided by the size of the sample, and take the square root of that. So that's 1.4 over 10. Divide that by 10, move the decimal over 1, so we're going to get 0.14 for our standard deviation for the sampling distribution. So notice the means are the same, but the standard deviations change. But we could analyze the sampling distributions with a normal curve now at this. And to see it, we could go over here to distributions. We'll just have this draw it for us. The normal curve, we put in our mean 6.8. We put in our standard deviation 0.14, and we go to next, and there's our distribution. That's what it looks like, normally distributed. Okay. So many of you are going on to college and thinking about that at this time. The mean room and board expense per year at a four-year college is $10,453. So that's a mean. You randomly select 9 four-year colleges, so that's sampling, right? Pulling 9 out. What is the probability that the mean room and board is less than 10,750? Different number here. We're told to assume that the room and board expenses are normally distributed. That's making reference to the population with a standard deviation of 1,650. So since our sample size is only 9, we would need the population to be normally distributed to be able to apply this rule that we've been doing, and it is. So it's normally distributed, so we can use any size sample. The mean is the 10,453, and the 53. Rewrite that. 10,453. The standard deviation given to us is 1,650. Okay. And then we want to see from our sample of 9 is what's the probability that this sample is going to have a mean less than 17,750. Okay, so we need our sample information. Remember, the mean stays the mean, so this does not change. The size of the sample is 9, so we'll put that there. And the standard deviation is going to be 1650 divided by the square root of 9. And we can get that from going to our calculator. It's 550. Now we could write that down and remember it someplace, or, well, yeah, we're supposed to write it there, so let's go ahead and write it. 550. We can also copy it so it's ready to use. The var key has copy on it, so we're going to go shift copy with it selected. Oops. Oh, that's the var. Let's go back. So let's highlight shift copy. There, now it's copied. We're now going to go to our distributions, and we can use the normal distribution, which we are here. We need to put in our new mean, 10,453. We need to put in our standard deviation of 550. Let's see if I get it copied. I can paste it in there. So shift paste, and then no, I don't want to turn it off. I want to go there. We want to see if it's less than 10,750. 10,750. There's a 70.54% chance that it is. So we could write that as a decimal, 4 decimal places, or we could write it as a percentage, depends upon whatever they're asking for. But that's the probability that the mean of our sample of 9 would be less than 10,750. Okay. Got 2 more examples we'd like to take a look at. So in this situation, notice these questions are going to be very similar, but there's a slight difference. So the first question, the average number of pounds of meat that a person consumes per year is 218.4 pounds. Assume that the standard deviation is 25 pounds. It's going to highlight these numbers somehow. So that's a standard deviation. This is the average number. This is the mean. And the distribution is approximately normal. Okay, so it's a norm. So we can use the normal distribution. Find the probability that a person selected at random, a person, so 1, consumes less than 224 pounds per year. So this is taking a population, taking one person out, not sampling, just taking a person out and figuring out their probability. This is not a sampling distribution, this is just the population. So for this one, we would just analyze it with the normal distribution. So let's go back. We would put in our mean of 218.4. Our standard deviation is 25. And this is not sampling at all, so we don't do anything to change or calculate the standard deviation. We want to find that they consume less than 224. And we've got it set at x less than. So that gives us that it would be a 0.5886 for that question. Now watch this next question, which is very similar. In fact, the first part is identical down to the end, approximately normal, so I won't read it again, but it adds this. If a sample of 40 individuals is selected, find the probability that the mean of the sample will be less than 224 pounds per year. So notice they're using the same number here, but since they took a sample, and again, we've got a sample of 40, which is more than 30, so that's good. But since the original is a normal, approximately normal anyway, we could have any sample size. So for this one, we do have our mean for our sample. It's going to be the same as the mean of the population, but the standard deviation of the sample is going to be the population standard deviation divided by the square root of the sample size. Okay, so we'll go back to our calculator. 25 divided by the square root of 40. Again, it's going to be this decimal number. If we arrow up and then arrow over, we've got it selected. Shift, copy, and then we'll be able to paste that in. We're going to go back to the distribution, and we're going to need the mean is okay, but the standard deviation is not 25 anymore. We're going to go Shift, paste. It's now 3.952. So that's our standard deviation. There, it looks like that. And now when we put in the 224, we want the percent probability it's less than 224. It's now 92%, 0.17, 92.17. So 0.9217 or 92.17%. This would have been 58.86%. Okay. So notice that even though the questions are very similar, we get different answers because sampling, the distribution is different. The standard deviation becomes different. All right, one more example to take a look at, and then you'll be ready to hit up and do all your homework problems on these. So find the probability and determine whether the given sample mean would be considered unusual. For a sample of n equals 39, so we've got our sample size. And again, it doesn't matter, we're bigger than 30, so this we can use, we know regardless of what the distribution of the population is, we'll be able to use sampling means. Find the probability of a sample mean being less than 12,748, less than, or greater than 12,751. And they give us this information here. Notice what they're giving us as far as the mean and the standard deviation, that since these have no subscripts, these are in reference to the population. So, but we want to find out about this sample, the probability of a sample mean being either less than this or greater than that. We're going to need to get this information. But the other thing is what they're asking for is not between two numbers, but the outside. So less than would give us this area here, greater than would give us this area here. So when we go to find this, what we're going to do is we'll actually find the middle area and subtract it from 1. Now you could find the lower area and the upper area separately and then add them together. That would work too. Or you could just take 1 minus the middle. We'll do that one. It'll be a little quicker. So the first thing we need to do is what is the parameters, and then what are the statistics, right? So the parameters come from the population. Those we were given as 12,748 for the mean, standard deviation of 1.6. For the statistics for the sample, the mean will be the same, 12,748. N is a sample size. We're given that as 39. And the standard deviation, what we're going to do is we're going to take that 1.6, divide it by the square root of 39, the sample size. 1.6 divided by square root of 39. That's the answer. We're going to copy it, and then we're going to go to distributions. We're going to go back. We're going to put in our mean, which was 12,748, and we're going to put in our standard deviation, which I forgot what it is, but I'm going to paste it in there. Now that I've got it pasted, I'll go ahead and write it here. 0.2562. Okay, and now with all the information in there, got our distribution. We're going to find the middle distribution, and then we're going to subtract that from 1. Okay, so the lower boundary is 12,748, which is the mean, and the upper boundary is 12,751. We get that there's a 50% chance that it's between these two, and so we're going to take that value, the 0.5. I'm going to copy that. I'm going to go back to the regular calculator, and I'm going to take 1 minus the number I copied, and we get it's 50%. So the left and the right give us 50%. There's a 50% chance that it would be outside of these two values. Okay, so basically the one thing we got to look at today is whenever we've got a distribution of sampling means, that we have to calculate the standard deviation of the sampling means using this formula. It's the population standard deviation divided by the square root of the sample size. So again, you'll see that again and again. That's the one thing that's new today. We can do this whenever the sample is larger than 30 or larger. Also, we can do this for any sample size as long as the population is normally distributed. So those are the things we picked up today, and hope you continue to make good progress.